This is an HP 5340A microwave frequency counter. And so a little bit of the backstory on this. So I got this counter. I've been wanting a while for my bench to have a frequency counter with a Nixie tube display. Just because, you know, everybody likes the Nixie tube displays. And I had the HP 5245, which was from some previous videos. And it's really kind of big. It's really noisy. And I know some of those things, you know, you can put a new fan in it and whatnot. But it only has a bandwidth up to 50 megahertz without using the plug-in extenders to extend the range to a higher frequency. And, you know, that's kind of neat and all, but I didn't want to fool with having to swap plug-in modules and do the, you know, dial it in with it and use it with the transfer function of those frequency counter modules. So I kept looking around, and I had known about these counters for a while, and I hadn't really ever got one. And so I had my eye on this one. I picked it up. But one thing about these counters is they have a real wide range. You know, this counter here will go from 10 hertz at the input here. Will go from 10 hertz to 18 gigahertz, and it goes that entire span from 10 hertz to gigahertz on one input, as opposed to something like this counter up here, which is the microwave counter from the previous video. You know, they split the frequency range into two inputs. You got a low frequency input here, which is 10 hertz to 500 megahertz, and you got a high frequency input, which starts at 500 megahertz and goes to 18 gigahertz. So with this counter here, you can't you don't have that range is split somewhat. And the way they do that on these counters is an HP a specialized hybrid sampling unit, which we'll take a look at in a minute. And for these particular counters, a lot of times what you'll find is that this high frequency input is blown because the input, that sampler input, is very easy to damage, and it's so easy they've gone ahead and put a caution label. HP puts this label on their units. Or if you input more than 30 plus 30 dBm, which is 1 watt of power, you will destroy the sampler of the unit. And what they say here is it's which is costly to repair, and that was back in the early 70s when they were making these counters. Now, as you could imagine, with the parts long out of production, it would be significantly more costly to repair. And if you read the manual, it actually specifies a maximum input power, and it says here on the front panel, maximum input power plus 7 dBm max. So a lot of times, what you'll find is people will permanently affix attenuators to these inputs, and the manual, a lot of times when it has you reading signals, it'll tell you to use an inline attenuator with the input. And some of the later models of this counter actually, the digital display ones, some of the later ones actually had an option where it came with a built-in microwave coaxial limiter to limit, if you had overpowered the input, it would actually limit the signal going to the sampler to protect the sampler. But anyway, this is an older unit, serial number 15. So it's a 1532 serial number. So that was would have been around 1975, I believe. And this one is unfortunately not equipped with very many options. It's got option 11, which is this HPIB output here. It does not have the option 1, which is the ovenized reference, and it also does not have, obviously, the option 2, which is the rear inputs, which that's fine. I didn't want the rear input anyway. The oven would be nice, but I've got some ideas, and we'll talk about that in a little bit, of how we can implement that option in this counter. It also has a label here that says option H10, which I can't find anything on it. I think that, you know, a lot of these this this gear had these kind of obscure options, H10s and H64s and whatever. And I think that it meant that they were categorized specially by HP for particular measurement at a particular, when they were calibrated at the factory, where they were assembled. The unit was characterized for certain operating characteristics. One other theory that I have, just based on from looking at the internet, is it may be that this was an ex-military unit, and they were specified for military use. Again, I don't know, I'm just speculating. But if somebody does have some info about those option codes, the H and the C's, and that you see sometimes, feel free to put a comment down there in the comments, and we can get that share that information. But anyway, so what we're going to do now is, as you may have seen, I've already taken the bottom cover off. And the top cover, I've taken the screws out. But we'll open the unit up, and we'll look at the inside here and see what we got to work with. All right, so we got the cover off, and we'll take a look here. We've got our fan here, and it is an exhaust fan. It's not a supply fan. And we've got our power supply capacitor bank here. All the power supply boards here, which all of the regulators are linear regulators. Because those obviously would be much cleaner output. And with the fan, of course, with the linear, you're going to get more heat dissipated across the pass element. So we got the fan here, and you can see a lot of these are mounted on heat sinks. So one thing that I know that we're going to be doing is these capacitors will all come out. This blue one here looks like it's already been replaced once, so that we'll take a look at that one. It may be newer. I know all of these capacitors here are original, and they will all have to go. We'll take those out. And I got to look in here too, and there's this bridge rectifier installed down here, and it looks like it was just wired into the circuit board. But in fact, when you look at the service manual, I've got a copy of the service manual. This is actually in the service manual this way, so it seemed kind of odd to do it that way, but that's how they did it. And there's some kind of little white crusty stuff on it, so I'll have to clean that up. The unit's is complete. It's got all the parts. Obviously, it was tested and verified working, and it is pretty dirty. I'll have to see if I can get in and get it cleaned up a little bit. But anyway, so our power supply section here. This is under this cover here is all of the high frequency portion of the sampler, with the sampler and the counters and the lock and the limiter. All of that stuff is under here. Our front end is here. Just a real quick look. So our high frequency input comes in here from this in connector on the front panel. First thing it does is it goes through a power divider, and then from there we go to we have two sampler assemblies here, and then these samplers here is the piece that gets damaged from putting too much power in. From there, it goes out into the rest of the unit. Our time base is here, which again, this is just the standard TCXO time base, and it just comes out on a little edge connector card right there, and it's got the frequency stamped on it, 10.000002 megahertz. So anyway, there we go. That's the standard frequency reference. And then on the backside here is the direct count board, which takes an input here. And then over here is our digital section. Right here is all of our Nixie tubes for the display. There's windows here and here for the indicators on the display. And then I believe this board here is the blanks out the leading zero board, or the leading zero digit on the display, so you just have the most, you don't have any zeros, you just have the most significant and then the display from there. We've got a resolution switch, a reset line. This is our sample rate, and it's, if you go all the way over, it'll go to hold, and then our two inputs and our range. There's also a check function. You can put it in check, and it should count the reference to 10 megahertz based on resolution, and you can change the resolution there. This is the part where the option 001, which is the high stability time base, is installed. There's a transformer that's supposed to go here, a voltage, a power supply circuit board that goes here, and then the actual reference goes here. So we'll take this out, and for the option 001, the unit, the manual specifies a this oscillator. It's a 10544 frequency standard, and that will go right in here. It sits down in there like that, and then that is, so with your frequency reference and your circuit board and your transformer there, that fits the option 01, and it's already wired. All you got to do is wire the transformer in, and the transformer gets wired back here to the line voltage switch. There's a circuit board that just plugs in, and then this just plugs in and bolts in, and then all the connections are already wired up under the chassis, including the on the display. There's an asterisk that will light up to let you know that the oven is cold, and when the oven warms up to the operating temperature, the little asterisk indicator will turn off. This is the frequency time base that I took out of that counter, the one that was missing the insulating material from the bottom down here. We took that apart in the last video and looked at it. So this is, I'm not going to use this this time base. The one that I'm actually going to use is over here. So we'll take a look at this one. So I purchased this unit. This is a used oscillator unit, and this is a 10811, which is the newer version of this frequency reference. And these, they're pin compatible. Some minor changes, but we can look at that, and we will address those if needed accordingly. But this is the unit that I actually purchased to put in this counter. It will go there, and then our power supply and transformer there. So we've got one of the pieces that we need to upgrade this counter. The other pieces that we need are the transformer and the circuit board. Circuit board, I intend to just design a circuit board that will plug right in here into this edge connector. The power supply circuit itself is not very complicated. It just uses a standard LM723 voltage regulator. It doesn't even need an external pass device because the current draw of the standard of the frequency oscillator and the heater elements are less than the capabilities of the integrated circuit, the LM723 itself. So we don't need a pass device. And so what I thought we would use for the transformer is, I've got this transformer here. This is a HP 9100 3067, and this transformer was removed from one of those parts counters, the 5342A, one of those parts counters. And this is actually the transformer that is used to supply the reference for when those counters are equipped with the upgraded time base. This is the transformer that is the power supply for it. So I know this transformer is more than adequate to supply the oscillator unit. And it's kind of odd that all these transformers are populated in those counters, whether or not that option is there or not. And what I think I'm going to do is I'm going to cut me a square of sheet metal that will fit in here. I'm going to mount this transformer probably on an angle like that, so that we clear this BNC here. And then I will attach it to the chassis with using these holes here, which is where the regular transformer would have attached there. And I'll just cut that sheet metal. I'll have to figure out cut some holes in that sheet metal to feed these pins through. I'll attach wire leads to these pins, heat shrink them, and then feed them down through the holes in the chassis down there, and from there we'll wire it up. So I think that's the idea I've got. It's definitely we should have plenty of room. You know, even if we have to stand it up a little bit, looks like maybe we might have, I don't know, so maybe like 3/4 of an inch or so of space. So we'll have to use some smaller standoffs, but that's an idea. Hopefully that'll work, and we'll see how that goes. All right, I'm gonna flip the unit over. We'll take a look at the bottom side, and then we'll talk about our first project, which is gonna be getting these can caps replaced so we can power the unit on. I haven't even powered it on yet because I know that the main filter bank is shot. So, all right, we got the unit flipped over now. Just a real quick look at the bottom side. There's not really a whole lot going on this side. Most of the everything's on the top side. This is the back plane for all of the counter boards that were under that can lid. There's a back plane, or I guess a motherboard for the power supply. So these are our power supply cards here, and then these are the main filter caps that will have to come out to be replaced. You got a power transformer, and then as you can see, our edge connector here for the time base power supply is already wired up. Some more edge connectors here for the digital, the display section, and then this is all of our input sampler section. And that's really about it for the bottom side. All right, here's the inside this the high frequency counter section. I've got the lid off, and these are all of the boards. As you can see, all these boards are in their individual cans down here to minimize any kind of interference. So you got to loosen these threaded pieces here, so they thread up here like that to make the board snug. So we'll loosen that down and pull this out. This is the limiter, I believe. And look at that. That is definitely not like anything that you see nowadays with that circular layout for that board there. But that's flipping through the manual, looking at these. You know, a lot of these just like regular old circuit boards, but that one kind of caught my eye as something that's definitely different. That is the let's see what that is. That one is the, yep, there we go, the A13 limit amp 1. We'll plug that back in. Yeah, this in here, the inside here looks pretty clean. Let's see if we can find one that's kind of loose. These all feel pretty tight. That one, there we go. So we'll take that out. Yeah, more of that. There's a onboard inductor right there with that spiral trace and some specialized integrated circuits. So hopefully that's not. And you know, like I said, this I expect this counter to work. Like I said, it was sold to me in a tested working condition. So, but all right. So I'm going to take these. I'm going to put this cover back on. Take these cans out. And I'll show you what I think is one way that we can put some more modern capacitors in there and replace those. And this is what we've got. So we've got two capacitors that are 4,000 microfarads at 15 volts DC. We've got 2 capacitors that are at 2,800 microfarads at 20 volts DC, and we've got 2 capacitors that are 2,200 microfarads at 30 volts DC. And all of these capacitors here look like they have a date code of 1976, so 21st week of 1976. So they may be, I don't really know. Let's see, I can pull out one of these logic boards. Let's see here. Looks like, let's see, date codes for these. I see this is 75, 45th week of 1975. There's another 1975. That one looks like 76, 76. And that one, let's see. There's another 75, 50th week, 1965. So somewhere in the late 1975, early 1976 era for this unit. But for the filter capacitors, so we got a little bit of a problem. So all of these capacitors are they're screw mount terminals to the board, and you can get this type of capacitor still. It is available. They're incredibly expensive to get this kind, and it looks like all of these. That one right there has got something hard, crusty stuff around the terminals, and this one does too, and that one does too. That one just a little bit. That one's got a little bit of stuff there too, and all. This is the newer one, the newer capacitor. It might be good. Don't unless that's a date code 1993, 1993. I don't know. But this would be the only one that I would say might be worth saving. These other 5 here, I'll throw away. But we got to figure out how to get something that's in a modern package into this opening here onto this circuit board. So what I've got is these more modern type capacitors. These are 4,700 microfarads at 35 volts. So those will work for the 4,000 microfarads, no problem. So we've got 2 of those. I've got some of these are 3,300 microfarads, 35 volts. So those will work for the 2,800 microfarad capacitors. Because I've got a bunch of them here, I'm going to use 2 more of these 3,300 microfarad capacitors. So we'll have 4 3,300s and 2 4,700 microfarads. So as we can see, just for size, that's what we're dealing with. So this is a much larger area than these modern capacitors, and more importantly, this terminal is a whole lot smaller than our modern, or than our older style screw-in capacitor. And I did a lot of thinking about how I wanted to do this. I thought, well, maybe I'd make a circuit board that would fit in here. But where would I attach it? Well, I guess I could use these mounting holes and some insulated standoffs and attach it there and sort of float it up over the chassis. But you know, then I got to run a bunch of leads. I got to run, what was it, 12 leads down into here to feed it back into the motherboard. I didn't really like that so much. So the only the best option that I can think of is I'm just going to put these in like so, and I'm just going to solder them onto these traces. So these are plated. These holes are plated. They're plated through to the other side, and I can put these capacitors in, bend the pins slightly over just so that they grip, and then I can just solder them onto the edge of this plated through hole. So I think that's what I'm going to do. It's you know, it's not reversible, but that's okay. I'm not going to spend $200 to replace all of these with stud mount capacitors. I didn't pay that much for the whole frequency counter, so I'm not going to spend that on the filter caps. I think I like this method. I'm going to do this, and we'll see how that goes. So what I'm going to do is I'm going to go ahead and assemble this, and then once we get it connected up, we'll take a look at how it looks finished, and then we'll power this counter up, and we'll put some signals through it and kind of test the operation, see how it's working. All right, so we've got the new electrolytic capacitors installed. One thing to keep in mind, you know, if you're going to be replacing these capacitors in your unit, is you need to pay particular attention to the polarity. Now they do this on the printed circuit board. There's a little triangle symbol imprinted on the board to denote the positive lead of the electrolytic capacitor. But you know, one would maybe just looking at it and not paying too much attention would think, well, the center, the long center trace down the middle would be the negative, but it's not. If you look at the arrangement here, they've got the capacitors arranged positive to negative to positive to negative. So that when you're installing your new capacitors, you're going to have one positive and one negative lead on that center. So that's what we've done here. So we've got our new CAN capacitors installed, and as you can see, we got one negative, one positive down this. This is that center piece, and you can see right here there's that little triangle right there, which denotes the positive lead for the electrolytic capacitor. And you can see they've got that for all of these electrolytics, and these are just too big, you can't see them, but they're under there. So we've got our two 4700 microfarad capacitors installed here, and I went ahead and like I mentioned, just went ahead and made all four of these be 3300 microfarads there. I'll flip the unit. This is just showing the arrangement of the original capacitors there, so that you get your values correct. And we'll flip the unit over. All right, we've got just looking at the back side here. As you can see, pretty much just did what I said I was going to do. Just orient the capacitors and then solder them to these plated through holes here, there and there. Now, you know, it's not entirely irreversible. You know, if you really wanted to, you could desolder these capacitors, clean the solder off the plates, and then reinstall stud mounted capacitors if you want. But now, more importantly, now that we've got this filter capacitors replaced, we can power the unit up and see what happens. All right, we're hooked on to the isolation transformer. I've got it set up, dialed in for about 25 volts AC. We'll look at the amps, and we're just going to turn it on, and we're just going to look for any sudden surges on the current ammeter. See if we have any problems. So we'll just flip that on. All right, and our current's showing very low. So I'm going to flip this off, and now we'll take this on up to full line voltage, and we will see how it goes. So we got that dialed up now. So we're going to power this on. Expect to hear the fan start up, and we should see some display on the front panel here. All right, I hear the fan going. We got a display on the Nixie tubes, and it's the gate's flashing, meaning the gate's it's looking for a signal. Let's put it in check mode. Alright, so in check mode, that looks good. We're seeing, for our full resolution, we're seeing our 10 megahertz reference. Let's slide it down to the next one, and of course that's going to increase the gate time because we're looking at higher frequencies. And down to, all the way down to 0.01 on the highest range there. And it looks like the switch is kind of dirty. We may need to, I'll get in there with some contact cleaner and see if we can get that cleaned up. Alright, so next thing we're going to do, so now we've got that in check, is we'll put a, we'll check the direct count amplifier. We'll put a signal into the direct, into the low frequency channel, and we'll see if we get our frequency on the display there. Well, we're going to use, for the direct count, we'll just use this signal generator. I've got it set for 100 megahertz with an output amplitude of 0 dBm. And we'll look at the display here, and the display is showing just probably right on 100 megahertz. Go ahead and take this up to we'll take this up to 250 megahertz. 250 megahertz, and we'll need to change our range. Take it down one, and there we go. So 250 megahertz. I really don't want to blow up the front end of this unit, as it should be working. So what we've got here is I've got a 10 dB attenuator in line with the input. That's going back to the same signal generator. We'll leave it set at 250 megahertz, and right now our amplitude's off, so we should have an amplitude of 0 dB. So we'll take that off, turn the RF on, and we're showing 0 dB of amplitude. Alright, and there it is. So we've got the lock indication. So this lock light will come up when it's locked, when the transfer oscillator is locked to the input signal. So that's good. It locks right away, so that's good. Go ahead and raise that up to 500 megahertz. Alright, and now we're showing 500 megahertz. Go ahead and go to the top, which is 990 megahertz. And there we go, 990 megahertz. Alright, we're going to use this signal generator. Now this one will go up to 3.2 gigahertz. So we'll go ahead and set that up now. 3200 megahertz, and we'll do an amplitude of 0 dBm, and let's make sure we got our modulation off. So modulation's off, RF's off, so let's go ahead and hook that up. Alright, so we're still looking at 0 dB output through our 10 dB attenuator. Now if we turn the RF on for that signal generator now, what we would see is we would see 2 and then something else down the rest of this way. So we need to switch the range up to we need to switch the range up one more. So now we're looking at gigahertz. So now we should see it's probably going to be 3.19 something after that. We'll see what it looks like. Let's turn it on. Alright, so we got RF on, and there we go. So that's pretty good. So now we've gone to the limit of this signal generator here. We can't go any higher on frequency. So now, but I want to go ahead and test to see if it will go all the way to 18 gigahertz. So what I'm going to use is I'm going to use this sweep oscillator. This is the one, I made a video about this one a few months ago. And I haven't really done much with it since I got it working. That was the big thing. I just wanted to get it working with an output signal. So I'm going to bring this down. We'll set it up on the bench, and we'll see if our counter here will go all the way to 18 gigahertz, because I know this this signal generator will. And now we have, so I got the sweep oscillator down, set up, it's powered up right now. The RF's turned off. Of course, we got the unlevel light because the RF's off, and we're set up for CW. And I'm going to feed. I'm going to turn the power level down here. We're still feeding through the same setup. I've got a piece of coax here going into the high frequency input through our 10 dB attenuator. I got the power level turned down. I think the maximum power out of this unit is somewhere around 8 or 9. I think I was getting somewhere around 8 to 9 plus 8 to 9 dB of output power. So I may actually have to turn this up to overcome the signal loss in the cable and the attenuator pad. We'll see what we get though. So we'll turn this on. Right now we're set for the low band 2.0 to 6.2 gigahertz. I'm going to go ahead and bring this. Actually, it was already dialed up there. I'm going to go ahead and put it down here around 4 gigahertz. So that's where we should be right now. Turn the unit on. All right, here we go. I'm going to raise on the CW knob here, and we'll go ahead and raise this up. All the way to the top of the band, which is this low band should be 6.2 gigahertz. Alright, there we go. So we're at the top of the band. And my little gigahertz indicator there. I've got the sampling time turned way down. That's why the gate slowed down. The gate, our little annunciator light is not blinking very brightly right there. So I don't know if that maybe a bulb issue, if it's an incandescent bulb, or maybe something with the drive transistor. Maybe I have to look at that and see if we can get that to indicate brighter. It certainly was brighter earlier. Let's see if we can maybe slow it down, or even put it in hold. Yeah, it's not. It's just barely sort of blinking there. Alright, there we go. So now we're at 12.4 gigahertz, and it's starting to show on the counter here. The counter's starting to indicate, so it wasn't indicating it. It looks like we lost it right there. So right around 13.4 gigahertz, 13.5 gigahertz. And there we go, we lose it. So what I'm going to do is I'm going to change the cable out. So what we did is I just changed out the coax. It's got this little shorter piece. This is some higher frequency rated coax. Still got the power level turned all the way almost down to the minimum there. We're on the 10 scale, and we should be somewhere around a little more than 5 gigahertz. 5 gigahertz there. And yeah, so that's probably 4.9 gigahertz, and it's over. We got the overflow light lit now, which is telling us that we're over the range. But yeah, we can switch it to our mid band here, 250 to 18 gigahertz, and we'll get the same indication there. We'll switch that back. Yeah, there we go. So yeah, 4.968 gigahertz. And we'll go ahead and take that up all the way to we go. So back at 18.76 gigahertz. I'm gonna dial it back down to 18 gigahertz. There we go. But yeah, that works good. So yeah, this seems to be working just fine if we get the right cable and the right attenuators in there. And I think I've actually got some attenuators that are rated for like 18 or 26 gigahertz. I'll just have to fish them out of my box over there. We'll hook those up maybe later on and do some more testing. But that's it. That's going to be it for this video. I try to keep the videos a little bit shorter than that last video. Was ran pretty long with the HB5342 counter. But like I said, the next step we're going to do is I'm going to look at some plans to get this time base upgraded. We'll get a board in here. We'll get a transformer set up for the power supply, and then we'll upgrade this frequency standard. Once we do that, so that'll be the next thing we'll do. After that, I may have some other ideas that I'm sort of throwing around, and we'll see where it goes from there. But yeah, I'm pretty pleased with this counter. I think it's going to work good, and it'll look nice here in the bench under these two, this power meter and this other frequency counters. And that'll be good addition to the bench, and we'll get that Nixie tube display that I've been wanting for a while. So that's it for now. Thanks for watching. If you have any comments, leave them in the comment section.